Hi, so I have a really fun problem that I don't know the actual answer to, but it may turn out to have a really simple solution. So if you have any ideas once you watch this, please put them into the comments down below. So here we have a language with a single string, just a single string only of A's, nothing else in the entire language. So obviously this thing is regular. So what I want to do is to find a smallest context-free grammar for this language. So obviously what you can do is have the start variable make the string a, and then a final a. So then here we have n a's, and then obviously this will do the job because this is a single string. We could just hard code it in right into the grammar. So what we're gonna define here is the complexity of the grammar. So the complexity of the grammar is going to be the following. So it's going to be the sum over all rules. What we're going to count here is the length of the right-hand side here. So here, in this case right here, we have n occurrences of the a right here. So then the complexity of this grammar right here, so the complexity is equal to n, obviously, because the length of the right-hand side is n. So let me show you where this can actually do better. So let's suppose that we wanted to get the language which is a to the 9. So there are 9 a's. So one way, obviously, we can go is the same idea. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So this would have a complexity of 9. I'm going to call it C for now. But we can actually do slightly better by having a different variable and another rule. So we would have S going to B, 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 and then the B here makes 3 A's. Okay, so each B makes 3 A's, and we have 3 of them here. So therefore, what we have here is that the complexity of this grammar is 6. We just add up the lengths of the right-hand sides. So what I want to figure out is, what is the complexity of this grammar in terms of n? Can we do better in general, or than just n? It turns out that we can, but how much better can we actually do? So there's one thing that I can prove right here, which is that the complexity of, actually I should define something first. So the C of n, I'm going to define to be the lowest complexity of any CFG for that language above, a to the n. Okay. So remember, this is a single string, not a whole set of strings. So what I'm going to prove here is that we can have C, the complexity of m times n plus d is going to be at most the complexity of n plus m plus d. And then maybe some other stuff after it, but these are the important pieces. So let's say that we had a variable a, and it did a bunch of stuff, and this was for the language a to the n. So the case of where n. So this is what we're saying right here. So what we can do to get m times n right here is we can do the following. So actually plus d. So what we can do is have the new start variable make d occurrences of the a. So there are d occurrences right here. And then we have m occurrences of the capital A variable. So this will make m occurrences. And if a makes little a to the n, then what this is doing is this is going to get m occurrences of a, so that gets m times n, plus d more of the a's, so that gets d right here. So what is the complexity? Well, whatever the complexity was of the a variable, we will add on m and then d. So here we actually can get right down to m plus d. So it turns out that this function doesn't grow very, very fast, but you can actually do better sometimes. So like for example, so let's say that I wanted to do this. So I wanted to do c of 9 times n plus d. So what we can do here is, let's say that we had the a variable makes some stuff. So again, as always, a makes the language a to the n. So now we're interested in making the string which is 9 times longer plus d, whatever d value we want. So what we're going to do here is this. We're going to have s going to 3 occurrences of a, and then what we'll have after is we're going to have s prime going to make d occurrences of the little a, just like before. So there are d of them here. And then we will have 3 occurrences of, not a, we will have 3 occurrences of s. So what is the complexity of this thing? Well, it's going to be the complexity of whatever n was. That's what the a variable made here. So then plus 3 plus, now we get 3 for the s and then 3 for the d. So now we're going to get 3 plus d. And so that's going to give us c of n plus 6 plus d. And that's better than this result up here, because we had 9 plugged in for m right here. But now we can get it down to 6. So the question is there something that we can actually prove in general? Well, here, this would actually imply, and I would like you to actually think about this, is based on the prime factorization of the number. But that's not necessarily the case, or at least I don't see why it's the case, because of this example. You can actually break up, it's something based on the prime factorization, but it's not exactly the prime factorization. So like, you could just put 9 occurrences of a, but it turns out that we can actually break them up even more. So maybe there's some way of breaking up the prime factors so that you take maybe a subset of them such that they multiply to the number. And then what you do is you add some a's in addition to that. There's a whole lot of things that you can do here. So I thought this was a really cute research problem. It's a really simple problem, really simply stated, but there might be something really complex here, or maybe there's a really simple solution. I have no idea. So I want you guys to help me out with this one. So hopefully that was interesting. Leave your thoughts about this research problem down in the comments down below. As always, please like the video and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. And as always, thanks for watching, and I'll see you next time.